Assalamu alaikum everyone. So in this lecture we are going to discuss about the very basic concepts of PCB designing, and we are going to learn how to design PCB using our software Proteus. So let's begin. So first of all, let's understand what is PCB. I think you already know what is PCB. PCB means printed circuit board. In general, to design circuits and implement them, we use PCB, right? This is the most professional way to design one PCB. Um, in a PCB, all the components of a circuits are embedded in such a way that we have copper lines which are called traces and pads, which connect all the components together in a very compact manner, right? So uh, most of the time, the type of board you are going to see in printed circuit board is called the FR4 boards. So this here is a FR4 board, and in FR4 board there are three layers basically. The top layer is copper, the bottom layer is copper, and in the middle we have an insulating material which is called FR4. That's why it's called FR4 PCB boards. So how to design one PCB from that FR4 board? What we usually do is we just try to remove some portion of copper using different methods, like using CNC, or another one is called the etching method. Using those, we try to remove some copper according to our design, so that we can place the components and the traces and pads are connecting all the components like this one, right? So this is one PCB, the complete PCB here. Okay, then um, then let's classify the PCBs based on different kinds of methods, like the manufacturing technology. Based on the manufacturing technology, PCB can be classified into two types. One of them is the through hole, and another one is the surface mount technology. Okay, so in through hole technology, all the components are going through the circuit. Okay, so you see some holes here, all the pins are going through our PCB, and we are soldering that on the bottom of this PCB, right? So this is through hole technology, and another one is the surface mount technology, which is a recent technology, and most of the time the circuits we see today are surface mount technology. So in surface mount technology, all the components are connected on the surface. Okay, all the components and all the pins are connected on the surface like this. Like let's say this resistor or this IC, all of them are connected on the surface, on the top surface. So this is SMT or surface mount technology. But for our purpose today, we are just going to design one through hole technology PCB. Okay. Then these PCBs can also be classified into several types based on the number of layers. So there is single layer PCB, double layer PCB, and multi-layer PCB. So what is single layer PCB? This From this picture we can already understand what is single layer PCB. There is only one layer of copper. In the top layer, we are seeing the coppers or traces which will connect all the components, but there is no coppers in the bottom layer, right? For double layer PCB, we will have two layers, one on the top, one in the bottom, and these kind of components or elements which are called vias will connect traces from the top layer to the traces to the bottom layer. So this connection is going through this via to the bottom layer. So this is double layer PCB, and for our demonstration today we are going to design one double layer PCB. Okay, then we can also design multi-layer PCB. That means more than two layers, maybe 6 or 7 layers. So here you can see one is the top layer, there is bottom layer too, but in between top and bottom layer there are several other layers which are connected through vias, right? So if I just count the layers, this is one layer, two, three, four, five, six. So in total there are 6 layers. So this is a 6 layer PCB. Okay, and then before going into PCB designing, we need to know some common elements found in a PCB. Uh, so first of all, trace. What is trace? Trace are basically the wires or the copper lines we see in our PCB which connects the components like this. This is one trace, right? Then next one is pad. What is pad? Pads are the portion of copper which are helping the components to be connected with our PCB. So here, this portion here, all the pins are connected with a pad in the PCB. Like here, this resistor here, this is connected using a pad in the PCB. Then via, this is the most important. Vias are basically here, this one is via, this one is via. Via will facilitate the connection from one layer to another layer. So let's say this is a two layer PCB. So this is from top layer and this is from bottom layer, right? So this via is actually connecting this trace from top layer to this trace of bottom layer. So this portion, this is pure copper, it will connect the two portion. But in general, in our country, this middle portion here that we have seen previously, this is not given because of our lack of technology, you can say. So we have to manually connect that. So how to connect that? We can just take a single core wire, as we see in a resistor, the legs of resistor. We can take that and place that here between these two holes, right? And solder here and here. So it will then connect the top layer trace to bottom layer trace. So in this way we can connect all the vias. Then move on to our silk screen. What is silk screen? Uh, the writings here you can see in the white color, all of them are silk screen. Uh, Very simple, I guess. Then solder mask. What is solder mask? In general, when you manufacture one PCB, at first this PCB should look like this. So bare coppers here. So these things, all of these things are actually copper, right? But this green layer here, this is put on top of that layer of copper, so that we can create an insulating layer. So this is insulated, that's why there will be no conductivity here. This is just for protection purpose. We can use solder masks if we want, but traditionally in our country, as this is a costly process and also sometimes we don't have that facility in most of the PCB designing factories, that's why we don't use solder mask. So this is an optional situation basically. Then let's talk about the IC base. So what is IC base? A very good example is this Arduino here. So in this Arduino, you will see that uh, the Arduino is not directly soldered onto our board, right? There is something, a plastic container which is soldered onto the board, and on top of that we can connect the Arduino whenever we want, and we can also remove that whenever we want. So that's the uh, basic advantage of using IC base. So it is replaceable on the event of IC failure. So if let's say your IC is not properly working, then you can remove that and replace that with another IC whenever you want. And also another problem when we are directly soldering the ICs onto our PCB is that sometimes when you solder the ICs directly, you may overheat them and damage that. But when you use IC bases like that, obviously there is no issues like that. So that's why it's better to use IC base rather than directly soldering the IC onto our PCB boards. Uh, so that's all for the basic concepts of PCB designing. And now we are going to learn how to design PCB using our software Proteus. So this is Proteus and we are going to design a PCB here. The circuit you are seeing, this is basically just a BCD to 7 segment circuit. So here in the input side you can see a 4-bit input which is the BCD input, and at the output we have a 7 segment display to show the output. If I just try to simulate it here, you will see that at the input, as A is the most significant bit, that means now it's giving 0 1 1 1 in the input, so at the output we should get 7. So we are getting 7 here. uh, Now our goal is to design a PCB based on this circuit. How to do that? Before we start, let's learn the basic things about our 7 segment display. This 7 segment display is basically just combination of 7 LEDs arranged in such a way so that we can see this kind of combinations, right? So A, B, C, D, E, F, G, and also another one which is for showing the dot. Now in the market you are going to see um, two kinds of 7 segment display. One of them is called common anode type, another one is called common cathode type. In common anode type, the VCC or high voltage should be common for all the LEDs, and to drive a particular LED you have to, let's say for example, if I want to turn LED A on, this one, then I have to give a logic low here so that VCC may go through this LED. In this way, uh, in this display all the LEDs are arranged. Okay, so you can see the pin numbers here, and we have two VCCs here at the top here and also in the bottom. If I use one of them, that will be enough. And for the common cathode type, the ground or logic low should be common for all the LEDs. That means to drive an LED, you have to give logic high to that particular pin. So for example, if I want to turn LED A on, then I have to give logic high to A so that current can flow through this LED up to the ground. Okay. So in this way, we can use common anode or common cathode type 7 segment display uh, based on our need for our project. So here in this design we are using a common cathode 7 segment display. Okay, and before we move on to our PCB designing, we have to make sure of one thing, which is whether all the components has PCB package with it or not. So when you search for a component, let's say if I go to component mode, then press P here. Let's say I am looking for 74HC 02, let's say for example. Then when I am getting this schematic here, also there's a PCB preview for that. There should be a PCB package for every one of the component we are designing when we are doing the PCB. So that has to be made sure. One other way to check that whether your component has PCB package or not is to double click in the component. Let's say for example, for this U6A component, we can just double click here. Then under the PCB package, we will see something written DIL14. So there is a PCB package associated with it. We can also click here, and indeed there is a PCB package with 14 pins, right? But unfortunately for our circuit here, the 7 segment display doesn't have any PCB package with it. If you just double click here, then you will see there's nothing under PCB package. So how to solve that problem? To solve that problem, we have two methods. One of them is in Proteus. Generally what happens, sometimes there is a schematic and there is a PCB package for that, but they are not properly linked. That's why it's not showing there. Then we can just link them to properly show them. Another way is sometimes you will see for some of the components in Proteus there is no PCB package. Then you have to make your PCB package yourself and then link that to your schematic or your component, right? So fortunately for our 7 segment display here, we have a specific PCB package. We can link that to our schematic here. So how to do that? To do that, first of all, double click here, then uncheck this one, exclude from PCB layout. Then you can press OK. So let's right click and press packaging tool here. You can press OK here, don't worry, then press add. Now you have to search for the PCB package for your 7 segment display. Let's write 7SEG. So you see there are some packages for 7 segment display. So the first one, single 7 segment display, 0.56 inch digit height, it can be used. So press OK. So now this is the PCB package for our component, and we have to match the pins, the PCB package pins and the schematic pins together so that we can define our 7 segment display. So we can link them like this. So to do that, we have to click here. Okay, in this column all the PCB package pins should go, and as this is pin A, it should be linked with pin A from this diagram, right? So let's look for pin A. This is pin A, right? So let's click here. If I click here, you see A1 is written here. That means pin A and here pin A1 is matched. So the schematic and PCB package pin got linked up. In this way, all the pins should be linked. For B, it should be B1, right? Let's press B1. Where's B1? Yeah, B1. Then C, C1, press C, then common pin. For common pin, we can use CA1 or CA2, whichever we like. So let's click CA1. Then D. For D, D1, then E. Now for F and G, there is a problem. If you look at the schematic here, F1 or F is the top one and G is after that. If you look at the actual schematic, you will see that the position of G and F are reversed in your Proteus PCB diagram, right? So we have to solve that. So F should be here, G should be here. So how can we do that? We can just change the position like this. So for F, I am going to click G, and for G, I have to press F. Otherwise, what will happen? You are going to get error. When you print the PCB, then you are not going to get the proper output because of this problem in the PCB diagram, right? Then let's press assign packages. Here, it will ask you to select a library where you will save your package. So you can choose any one of them. Let's choose user DVC and press save packages like this. And it will ask, do you want to update the devices in the design with newly packaged device? Yes, we want to. Yes. And then if you double click here, now it has a PCB package, right? Which is this one, 7sec56. So in this way, we can solve that problem. And if I don't have any PCB package like that in our Proteus, then we have to build it ourselves and then link it with our schematic, right? Okay, then let's talk about the connectors here. Obviously, we can't use this kind of logic state or logic probes to uh, design our PCB. There should be some kind of connectors so that we can practically connect some signals to our PCB, right? So let's discuss about that. In general, to give power to any PCB, we can use this kind of terminal blocks. These are called terminal blocks. So we can use in our PCB this kind of terminal blocks to give power, and to get this kind of terminal block, we can write T block in component search mode. Okay. For signals in PCB, we can use this kind of headers like this. This is male header and these are female headers. These can be used, and uh, we can connect jumper wires with them, right? We can also use these kind of connectors for signals. These are called JNC ST connectors. Okay. uh, so the advantage of using this kind of connectors is that it has a locking mechanism like this, right? Now let's replace these logic states with appropriate connectors. So let's search for CONN dash SIL. So these are the connectors with different number of pins, right? So for our case we need 4 pin connectors. So let's check this one. So let's take this one, then we can just place it here, right? Like this. Rotate it, then place it here. We can just connect all of them like this. Yeah. Okay, it's done. We can also change the name. Let's call it BCD input. Okay. Then we have to give the power for the whole circuit. For giving power, we have to take terminal block. So let's search for that in the components. So let's write T block, TBLOCK, and we are going to take 2-pin terminal block, as we are going to give power and ground to the whole circuit. So let's double click and place it here. So we will place it here. So now we have to give power and ground to the whole circuit. All the gates you are seeing here are just part of some IC, right? So U4, U2, U2, these all are actually part of some ICs, and all the power and ground pins, that is pin 14 and pin 7 for most of the logic ICs, these are hidden here, but internally they are connected to power and ground. That means if I just take from terminals mode here power and ground, then connect it with this one. Okay, so let's take power and place it here and ground here. Okay, if I just connect it with these 2 pins, that means this power and ground is internally connected with all the logic ICs we are using in this circuit. Okay, because internally this power and ground is already connected. And also, as you can see, this ground for the common cathode 7 segment display, this is also connected with this one because of the logic of our Proteus, how it works. Okay, now let's also change the name here. Let's say this is power. Okay, so we are done in the schematic portion. We are done with all the things. We can move on to our PCB layout now. To start designing our PCB, we can just click here in the PCB layout, then it will create a window. Here we can design our PCB based on the schematic we have already done. But before we start, we have to understand the layers here. So you see at the bottom left we can see all the layers. So top copper is red one, blue is bottom copper, then light blue is top silk, and another important one is the board edge here. In between them, all other layers are not that important right now. So first of all, to design our PCB, we have to create the board edge that will define the dimension for our PCB, right? So for that, we have to click here to create a square box, 2D graphics box mode. Press here, then go to your layer selector, then click board edge. Then go to the center, click here, then you are going to create a square board edge for your PCB circuit, right? So at the bottom right, you can also see the dimension of your box. Right now it's 80 millimeter length and 45 millimeter in width, right? So let's take somewhat like this. What is that? 130 30, let's say, and here maybe 70. Okay, so 70, 130, yeah, this one. Then click again. Now your board edge is created. We can place all our components here. Another interesting thing of our Proteus is we can visualize this PCB anytime we want in 3D view. How to do that? Right now only the board edge is created. That means we will see just a bare square board here. So to do that, we have to press here, 3D visualizer. If you press there, you will see a green board is being shown. We can also move that if we want, like this. As we place all the components here, all of them will be shown here one by one. Okay, so let's close that. Now let's place all the components here. So for that we have to uh, click components mode. Here all the components are being shown one by one. We can place all the components. Okay, so let's take um, the connector first. Okay, so let's take the connector. We can just rotate the components using minus button in the numpad. So let's do that. Okay, like this maybe. Yeah, let's place it here. So this is the connector, 4 bit BCD input connector. Okay, then let's place the terminal block for power. Okay, like this. Then we can place all the IC one by one. So U1, let's select it here. Okay, we can rotate this if we want. Yeah, here, let's place it here maybe. Okay, then U2, let's place it here. Right now I'm not worrying about the alignment. We can solve that later on. So U3, let's place it here. Okay, then U4, let's place it here maybe. Then U5, let's place it here. U6, then U7. I'm just randomly placing. I know we have to worry about the orientation because these yellow lines are showing the actual connection between the components. That means you have to think about how you are placing all the components with respect to each other so that the connection is easier. But we have a method for solving that. I will show you that. Um, and in general, our circuit is very simple, so we don't have to worry that much for the placement of our components because there will be no unsolved connections. Okay, so all the components are placed. Now to align them, let's say if I want to align these 3 components, select all of them, then press Ctrl A. So we will have a dialog box like that. Using that we can align them vertically or horizontally, whichever we like. So these 3 should be aligned vertically, right? So vertically, it's already selected vertically. So okay, it's already aligned. Okay, for these 3, let's select all these 3, then press again Ctrl A, then align them vertically. Okay, then here also these 3 center vertically. Yeah, then horizontally I can align them, align these 3, Ctrl A, center horizontally. Okay, okay, it's done. Then also for these 2, Ctrl A, center horizontally. For these 3, center horizontally. Okay, so now I can select all of them to place them in the middle maybe if I want. Okay, now we can place all the resistors and the 7 segment display. But wait, we don't have any 7 segment display here. Yeah, this kind of problem might happen sometimes. If you go to the schematic capture, you will see there is no name here, so there should be a part name. If you write here the part name, let's say for example I am writing display. Okay, so then this is display. Now you will see that the components is showing, so every part should have a name so that the components are shown in the PCB layout. Okay, so now we can place all the registers. R1, let's rotate this one like this. Yeah, then R2, R3, R4, R5, R6, R7. Yeah, like this. Then let's place the 7 segment display. Okay, now let's try to optimize the space somehow. Okay, I can just select all of these three, then move it here downward direction. Maybe also, yeah, like this, right? Yeah. Then I can move them closer like this, maybe, and rotate it. uh, yeah, maybe here, and this here, also rotate it here. Yeah, then I can optimize the space everywhere like this. Keep it here. Sorry. Okay, I can move it here like this. Yeah, I guess so far so good. Now we can also optimize the connection here, the connection between all the components. How to do that? Just click tools here and then press Gateswap optimization. It will ask whether you want to run or not. Press OK. You see some connection just changed. How does that happen? Basically, in each of these components or each of these ICs, we have 4 or 5 gates inside of it, right? So it tries to change the connection there so that we can optimize the connection between the components so that our routing will be easier. Now if I again go to 3D view, you can see all the components are showing, right? Okay, so all the ICs and also 7 segment display register, everything is showing up. uh, Now we need to do one thing, which is, you see the pads here, these are called pads. These are the portion of PCB which will connect the components with our PCB, right? But the size of these pads are very small, and in general in Bangladesh our technology is not that good. So whenever you use this kind of small pads, sometimes it gets removed from the PCB. That's why we need to use larger pads, something like this. Let's say uh, click here, deal pad mode here. Then there are three kinds of pads. We will take this one, STD DIL, this one. So we can just replace all the pads with this one. So let's click here, then here, like this, to change the pads. Okay. So we are done with placing all the pads. Now we can see the 3D visualizer again, and you will see it's looking much better now. Let's press here to show the components or remove them. So you see, we can see the whole board without the components also, and the pads are looking much bigger. So let's close that. Now we can move on to uh, connecting all the wires, that means placing the traces, right? But before that we have to manage some design rules. So under technology, click design rule manager, then they are in net classes. So what is design rule manager? Before we connect all the traces in our PCB, we have to define some rules, like what should be the width of our traces, what should be the distance between all the traces, and what should be our via size. This kind of thing should be defined before we go on to our routing, right? So under the net class you will see two net classes like power and also signal, right? So power means all the connections that are coming from terminal block, power terminal block, and going to all the components power and ground. These are under uh, power net class, and all the other traces are basically under signal net class. So obviously we need more power or more trace width for power net class, right? So you see all the values here written like T40, V70, something like this. This T40 means 40 thou, 40 thousandths of an inch. This is 1 unit, right? So to calculate the trace width that we need for our design, we have to do some calculation. So how to do that? Here, this is an online PCB trace width calculator. Depending our need and the material of our PCB board, we can calculate how much trace width there should be for our design, right? So let's say I am just being optimistic. I want 1 ampere current to flow through our trace, and generally our board has the material of thickness 1 ounce per feet square. Then if I take all those value, then results for external layers in air, because our layers will be external on the air. So that's why we are going to get this value. And let's change the unit to millimeter, then we are getting zero point 0.3 millimeter, right? So let's convert that to thousandth of an inch. So zero point 0.3 millimeter is equal to 11.811 thousandth of an inch. So if I take T10 trace width in our Proteus, that will be enough. But the problem with our design is that in general in Bangladesh, if you use T10 trace width, uh, the PCB designs are not that good. They are very fragile. That's why sometimes the traces get removed because it's very thin. That's why we have to make our trace width wide enough so that it doesn't get removed. So general rule of thumb for our design is to use at least T20 for our trace. So I will use T30 for power, and next style doesn't matter. It can be kept as none, and via style I'm taking it as V70. You should be taking V70 or V60 at least. Other than that, same thing will happen. The trace or the via can get removed because of that reason I mentioned earlier. So this is for power, and for signal we can take like maybe T20, okay, and via style V60. This can be taken, and you can see we are using only two layers, top copper and bottom copper. Other layers are given none. And we have to take via type through hole, obviously, for signal also, for power also, because we are using through hole technology, right? So let's click OK. So before we move on, we need to understand what is CRC error and DRC error. Okay, CRC means connectivity rule check. So in our PCB design, how many connections are missing, that can be seen by CRC error. Here this is CRC error. Right now 90 connections are missing, that's why it's showing 90 missing. And DRC error is basically design rule check errors. So right now we have given some rules from our design rule manager. If one of those rules gets broken, then we will see some DRC errors. Okay, now we can start auto routing. So what is auto routing? We can manually route the connections ourselves like this. So this is the traces track mode. We can click here, then place the tracks or traces ourselves. So I can just place it here, then move on like this, then click again, again, again like this up to here. So our connection is done. Or I can do something like this. Click here, then to go to the next layer. So right now it's in bottom layer, right? To go to the top layer, that means the red traces, I can just double click here, it will create a via, then I'm moving to our top layer. Using the top layer I can go here, right, like this. So manually we can create the traces ourselves like this, but it is a very cumbersome process. We can also auto route these things. We have an auto router here. So under tools here you will see auto router, and here uh, a lot of settings are given, but we don't need to change any of them. We can just start routing here. Yeah, let's click here, begin routing. It will start routing simply. You see, connection is already done very simply, very easily. So let's look at the 3D visualizer. So here we can see it's showing the whole connection. Let's place the components also. But there is some problems. If you look closely, you will see that there is some problems like this one. Uh, so here, for this one, the traces are coming from the top copper to our pads, right? So if you need to solder them, you have to solder them from the top layer. But as there is a component here, if you try to solder it here, then obviously you will damage our connector here, right? So how to solve that problem? Obviously, to solve that problem, all the traces should come from behind here like this. Okay, so that we can easily solder them from the bottom, and all the components should be at the top layer, and all the soldering and all the traces should come to our pads from the bottom like this and like this. But if I have traces like this here, obviously it will cause some problem because we will have IC base here, and if you try to solder in the top layer, obviously your IC base might get damaged. So that's why we need to have some solutions for that. How to do that? So to solve that, one idea is something like this. These pads here, these are actually for both the layers, top layers and bottom layers. That's why the color is purple or pink, something like that. But for bottom layer, we know the color should be blue, and for top layer, that should be red. But the pads here has actually both layers. That's why when we go to our 3D visualizers, the pads are showing in the top layer and also in the bottom layer, right? So if I just take one layer, so if I do something like this, let's take DIL pad mode, then STD DIL, then right now it's selected all layers. That means top and bottom layer, both of them. If I take bottom layer here, then replace those like this, then it might work, right? Because then obviously we will have only bottom copper, so no traces should come from the top layer to our pad, right? So let's try this solution and hope that works, right? Before that, let's remove all the traces from here. Okay, so I can just undo everything and then replace all the pads again. So from here, let's start like this. Let's also change the pads here. So round through hole pad mode, this should be selected, and you have to match the size. Like I think this should be this one. Uh, yeah, this one, right? So you can just replace those with bottom layer pads. Also for this one, right? So for this one, stddl. And for this ones, the square ones, and match the size. Very small, so let's take something bigger. This one maybe a little bigger than this one. Yeah, this one. This should work. And for this one, the circle ones, I think still bigger than that. This one maybe. Sorry. Yeah, this one. So it's done. So we have replaced all the pads with bottom layer pads, and let's make our design more compact. I think we can do that, right? This is possible. Uh, let's do that. Yeah, move them to left. Yeah, this can be done now. Change the size here. Yeah, and we can move the size here also. Yeah, like this. Then move them closer. Then change the size here, here, and here. Okay, I think it's looking good. Yeah, now let's auto route. Tools, then go to auto route. Begin routing. So you see, even after that, there is some DRC error. That's the problem with this one. For this solution, you'll see that some of the top layer coppers will go through the holes itself. I don't know why that happens, but it has always happened with me. So uh, I have another solution for that, the final solution, which will work for this case. So let's try them out. Okay. So the solution is very weird, but bear with me and try to understand the logic. So let's take our track mode, then let's take top copper from here. Okay. So the idea is that if I just draw a square trace like this with top copper like this, then obviously no top copper trace can overlap this one because of the DRC error, right? So we can just do this for all the components here. So let's just copy this one, select this trace, then copy route, then place it everywhere, wherever you need. Okay, like this, like this. But one thing to remember here, if I just show you again, click track mode, then top copper, then create a square trace, right? But if you touch the traces, then it will vanish again like this because it is short circuited, right? So that's why it vanishes. So that's why you have to create a square trace like this, but you have to keep some gap here. So click here, then right click. So it's done like this. So you can do this for all the components, right? So again, copy route, then copy this to all the components. You can always remove that. After auto routing, you can remove this portion, no problem. This is just for this is just for solving the problem. Okay, then same thing should be done for this portion also, right? So let's take track mode, then top copper, then this one. So from here, like this, like this, like this, like this, then go very close to that, click, then right click. Yeah, like this. So we can actually do this for resistor also, but if I look at the 3D visualizers, you will see that for resistors, we can solder it from the top and bottom. Both is possible. So that's why we don't need to worry about this one. We can just omit about the resistor, but you can also do that if you want. Let's say I'm doing that. Uh, so track mode, top copper, then like this. Okay, then same thing for this one also. This one also. Okay, so it's done. Now we can auto route the whole thing. Let's click tools, then auto router and begin routing. Let's see what happens. Okay, so it properly worked, but still two DRC errors. Let's check what are those errors. Yeah, so because of this one, I think this can be solved. This is no problem actually. If you can just delete that, you see, yeah, it's just because of the extra layers or extra traces we have given. So now we have to remove all the extra traces we have created before, like this one. We can just delete that. Just click here, then press delete. Click here, press delete. Click here, press delete. Click here, press delete, like this. In this way, just remove all of them. So all the extra traces are removed and it's properly done, I guess. Let's look at the 3D visualizer. Yeah, it's looking very good, right? And no traces are coming from the top copper to our pads. So our issue solved. Yeah, good. So this is our top view. So you can also write your name inside your PCB, okay, using top silk, let's say. For that, we have to click 2D graphics text mode and also change the layer to top silk, okay. Then we can press anywhere to write anything. Let's say I want to write here something. So prime implicants. I want to write prime implicants. Implicants. Yeah. Then I can press OK. And yes, this can be written here like this. Okay. So if I look at the 3D visualizer, you see, in this way you can write your group name here in the PCB boards. So now just one last thing you can do here, which is to show the dimension of the PCB board. For doing that, you have to click here dimension mode and check the board edge here. So take the layer board edge, then you can show the length here. Click here and from here to here you can show the actual dimension of your PCB. So the length is 126 millimeter and the width should be, you can click here up to here. So width is 56 millimeter. So this is our complete PCB, and this is how you should design a PCB. I know the process was very complicated, but if you follow this process, I think all of your PCBs will be flawless. So that was all for this lecture. Thank you.